Today we're going to continue our discussion in section 4.1. You'll remember we did some real math at the end, right? Stuff where you had to figure something out that you didn't know, and there wasn't a strategy in which to do it. You just had to try and see if you could figure something out. So believe it or not, that's how most of the wonderful theorems and things start when a mathematician creates them, is that they're trying to figure out, why is such and such always happening? When does it work? When does it not work? So you participated in a true, like a math discovery kind of activity. Before we had done that, we had taken a look at some divisibility rules. I'm just going to run through them real quick to remind you of those, because we're going to jump in with an example of those. So there's a number of different rules. They aren't all of the numbers. Like, you notice that we don't have a divisibility rule, for example, for 7. There just isn't one. But there are for several of them. So the first one we had was divisibility for 2. It ends in an even number, namely a 0, 2, 4, 6, or 8. Divisibility test for 5, much the same, ends in a 5 or a 0. And for 10, it ends in a 0. So these all have the same sort of a nature to them. 4 and 8 are actually akin, likened to the divisibility test for 2s. When you look at the divisibility test for 2, you look at the last digit to see if it's divisible by 2. When you do it by 4, you look at the last 2 digits as a 2-digit number to see if it's divisible by 4. And if you have divisibility by 8, it's the last 3 digits as a 3-digit number to decide if it's divisible by 8. 3 and 9 are much alike. For 3 and 9, we actually add the digits together. And if the sum is divisible by 3 or by 9, then the original value is divisible by 3 or by 9. And the last 2 were divisibility for 6 and for 11. 11 is the awkward one to write out, but the process by which you really do it is you skip every other digit and add them together. And then you add the remaining ones that you skipped and add them together. You find the difference, that is the subtraction between those 2 sums. And if that value is divisible by 11, the original number is divisible by 11. And then the last one was divisibility by 6, which is where we sort of stopped and stayed for a little while. And 6 actually is simply that it's divisible by 2 and 3. And it has this feature that we discovered last time, that it's applicable in other situations. It's not unique to the number 6, but it is unique to any value that we can break down into 2 numbers that have no common factors. So we did an example like 5 and 3 make 15. So 15 would work. I can break it to 3 and 5. 24 is a really cool example because 24 can be broken down to 8 and 3, which work, but it can also be broken down into 2 and 12, which don't work. So you have to be a little bit careful how you do the breaking down. It's not about the number, the 6, it's about how it's broken apart and whether or not it will work. So that was divisibility rule for 6. So what we're going to do is we're going to take an actual example. The number is 24,015. And we're going to answer the questions of, is it divisible by 2, 3, 4, all the way up to 11? Obviously, we don't include the things we don't have tests for. Notice there's no test for 7, so we don't have 7 in this list, right? So while it's perfectly acceptable for you to check and actually grab your calculator and say 24015, hit the division button and put 2 just to make sure that you were correct in your assumption or whatever, your justification has to be based on the properties that we just discussed, all right? That's the point. So when we're looking at 24,015, is it divisible by 2? No. And why not?
Because the last digit is an even number.
Right, because 5, the last digit, I'll say the last digit. The last digit's not even. How about 3? We're just going to go in order.
Yes.
It is. Abby, how did you decide?
Because if I was to add all those digits together, it gets me 12, which is divisible by 3.
Okay, so all the digits added together is 12. That's what Abby said. And it is true that 3 divides 12. Remember that notation we talked about last time? Read it from left to right. That vertical bar is read as the word divides. 3 divides 12. So 3 will divide 24,015. Very good. There's actually an interesting thing that happens when something's not divisible by 2. If it's not divisible by 2, it's not divisible by any even number. I mean, it doesn't have a factor of that's even, so it can't be divisible by any other even number. So we almost get everything on this list that's even now just for free. We're still going to justify it with the properties that we have, but we should know 4, 6, 10, 8, all of them are even. They're not going to divide it because the number itself is not even to start with. We're going to use the properties. So why is 4 going to be a no from the properties we discussed?
Because the last two digits aren't divisible by 4.
Right. So the number 4 does not divide the last two digits, which is 15. Right? It just doesn't. And the property was that if it's divisible by 4, the last two digits have to be divisible by 4. That's the only way it works. So 4 does not divide 24,015. The next one's 5.
Yes.
Yes. How come, Emily?
Because it ends in a 5.
Right. Because it ends in a 5. Okay, why is 6 going to not work? Right. So in order to be divisible by 6, it has to be divisible by 2 and 3. It works for 3. It fails for 2. So this one's a no because 2 does not divide the 24,015. And we already justified why 2 didn't do that. The next one on our list, I believe, is an 8.
No, because the last 3 digits aren't divisible by 8.
Yeah, and you'll notice that I kind of cheated in giving you something that's easy to see the last 3 digits, right? Because it starts in a 0. Because 3 digits are not always easy for us to see if they're divisible by 8, but this one works. The last 3 digits, this is an 8. 8 does not divide the 0, 1, 5, namely the last 3 digits. Because it's really just 15. So 8 does not divide 24,015. How about 9?
No, because the digits don't add up to something that is divisible by 9.
All right, so it's the same rule as 3s, right? We add the digits together. So 2 plus 4 plus 0 plus 1 plus 5, which is what we got before, is 12. 3 divided 12, so it was good to go for 3, but 9 does not divide 12. So 9 will not divide 24,015. 2 more. 10. No. Who said no? Emily, how come?
Because it doesn't end in a 0?
Yeah. Doesn't end in 0. And then on 11, we need to do some work to double check. So a lot of things are not divisible by 11. That's an uncommon factor for things, generally speaking. But we'll check it by taking the numbers. We have 2, 4, 0, 1, and 5. So we have 2, 0, and 5. What's the sum of those? 7, right? Yeah. And then the in-between ones, the 4 and the 1. The sum of 4 plus 1 is 5. And 7 minus 5, which is 2, does not divide by 11. Okay, so if this value here at the end had been 0, we would have been good. 11, we would have been good. 22, we would have been good. But you can see that's not very many digits out of all the possible things it could be subtracted to get, right? So it doesn't happen all that often. So this is no, because we did all this below. So this is the y. And 11 does not divide 2. That's what the ending result is. 11 does not divide 2. So 11 does not divide 24,015. And again, if you wanted to confirm, make sure that all of your answers make sense from just, the calculator's perspective, so to speak. You could run through and you could actually take the 24,015 and divide it by each one of these digits, and the yeses and nos should match. Justifications it doesn't help you with, but it would help you to know that for sure your yeses and your nos were correct. Any questions on that? Okay, So I ran through all of our divisibility rules with specific numbers. I also want to go back and remind you of one other thing that we did last time because we're about to use it on a couple of examples. We talked about theorem, in particular 4.1 and 4.2. 4.1 has this beautiful feature that if a number divides something, right, like 2 divides 10, then it's going to divide all multiples of 10. So multiples of 10 you can be thought of as like the multiplication tables you learned. Everything that you comes out of, multiplying by 10 would be also divisible by 2. And then these had to do with adding and subtracting values. So if both numbers are divisible by a number, right, so if A and B are both divisible by D, then their sum is. If one of them isn't, then their sum isn't. And then subtraction works the same way. If both of them are divisible by D, then the subtraction, bigger minus smaller, will work. And the last two are just flip-flops of each other in terms of the way they're structured. But they're saying if we have one of them is divisible and the other one's not, then when we subtract them, that the subtraction will also not be divisible by D. So thinking about that and some of our divisibility rules specifics that we did before, we're going to take a look at a couple of different examples that interweave a lot of that together. So number 2 says to classify as true or false. So if I ask a question about classification as true or false like this on a test, I'm going to tell you have to justify why, right? You're going to get that whole word explain. That means with words, something like that. So as we practice this, we're going to write that down. If your book does not tell you that, I don't want you to be penalized for it in your homework. Hopefully you're thinking through the why, but if you don't write it down because it didn't tell you to write it down, I'll accept that, okay? So the first one says, if a number is divisible by 6, then it is divisible by 2 and 3. That is true. And we'll talk about that in a second after I do part B. Part B says, if a number is divisible by 2 and 3, then it's divisible by 6.
True.
That is also true. So both of these are true, and they are ramifications of some of the things we were talking about, specifically about the divisibility by 6. But really clearly, they're simply an application of what the divisibility for 6 says. Do you see this statement that says if and only if? If and only if in mathematics is a very interesting statement because it means it goes both directions, right? It says a whole number is divisible by 6 if it's divisible by 2 and 3. And then you can read it the other direction. A whole number that is divisible by both 2 and 3 is also divisible by 6. Like you get to go both ways. The if works both ways. So knowing that you have it divisible by 6 means for sure it's divisible by 2 and 3. Knowing it's divisible by 2 and 3 means for sure it's divisible by 6. So you get both of these on this one simply by the divisibility rule. Of 6. Okay, so there's not really a lot of justification that has to happen for that particular one. But this is showing up in sort of contrast to what's happened next. The next one's talking not about 2 and 3, but about 2 and 4. So if a number is divisible by 8, then it's divisible by 2 and 4. Is it?
True.
It's actually true. Let's just about justify the why in just a second. But let's go the other way. If a number is divisible by 2 and 4, is it also divisible by 8? That's false. So why does it work in one direction and not work in the other? Well, the reason it works on the first one on C is because when you take 8 and you divide it down, you get the 4 and the 2. So you can always work from the top down. Something larger breaks down, it has to divide by the smaller facts. If you think about it this way, think about your multiplication tables of 2s, all the even numbers, right? 2, 4, 6, 8, 10, all of them. All of them include multiples of 8. Right? I didn't say that quite right, but all the multiples of 8 are included. Right? 8 shows up, 16 shows up. They all show up because they're simply even, right? You can do the same thing with the number 4. All of the list of 4s, 4, 8, 12, 16, all that list of 4s, the multiples of 8s are included everywhere in that list of 4s. Or you can think about it going straight from the multiples of 8. Your multiples of 8, 8, 16, 24. They're all even. right? Yeah, for sure. And they're all divisible by 4. Absolutely. So we can take something that's large and break it down into pieces that are not, I keep trying to not use this word, I'm just going to use it. The word's relatively prime. They don't have any factors in common. We're going to actually write down that definition at some point. I don't think it's today. I think it's in 4.2 or 4.3. But the two numbers are considered relatively prime because they have no factors in common. So we can break it down into values that are not relatively prime, i.e. they have factors in common, and the numbers will still be divisible by 4 and 2. So we can do that. It's the building back up that we can't do. So if we took a number that is divisible simply by 2 and 4, and that's all we know, there are lots of numbers that are divisible by 2 and by 4 that are not divisible by 8. Can you give me an example of a number that's divisible by 2 and by 4 and not divisible by 8?
12.
12 is a good example. 12 divides by 2. 12 divides by 4. 12 does not divide by 8. It's not the smallest example, though.
4.
4 would be your smallest example, yeah. 4 would be one. There's infinitely many numbers we could pick. Basically, we need values that are multiples of 4, because by automatically, they're going to be divisible by 2 on this one. So we need values that are divisible by 4 that are simply the in-between of the 8s, right? So between 8 and 16 was 12. It's halfway in between. It's divisible by 4, but not divisible by 8. So there's lots of examples that we would have that would be divisible by 4 and by 2 that do not divide by 8 when we go in that order. So you can take something large and you can break it down into its pieces always. But you cannot always take pieces and work your way back up to their product. That doesn't always work. And that's actually what we were noticing last time. So if we think a look at our list over here that I made, our list on the left, numbers that worked, would work in both directions. So that example that we just did that said if a number is divisible by 6, then it's divisible by 2 and 3, and vice versa, would work for everything on this list. If a number is divisible by 4 and 9, it's also divisible by 36. If a number is divisible by 36, it's also divisible by 4 and 9. You can do everything on the left-hand side. On the right-hand side, they work like the problem C and D that we just did with the 2, 4, and 8. Just because the number is divisible by 2 and 4, that's actually my first example, does not mean that it's divisible by 8. But if it's divisible by 8, it is divisible by 2 and 4. And you can do that for all the numbers on the list. The number 40. The number 40 is always going to be divisible, and all of its multiples are going to be divisible by 10 and 4. But there are things that are divisible by 10 and 4, namely 20, that's not divisible by 40, right? So you always have the ability to break it down in a way that you have missing pieces if you try to merge things together that are not relatively prime. That is, they have factors in common. All right, let's go back. So on number 3, we're going to take a look at some values that the goal is not to sort of make this harder than it is. It's to consider the values that were given as they were given them. So if you take a look at 34,051, and you want to know if it is divisible by 17, hopefully you see something at the very beginning, namely the number 34, that you know divides by 17. Does 34 divide by 17? It does, evenly. It's divisible by 17, and it's 2. It goes in evenly twice. And whether you recognize it immediately or not, all that means is you need to know if the 51 works. So is 51 divided by 17? And the answer is yes, it's divisible by 17. It's 3. And your calculator can assist you in that, but what it's actually doing is breaking it apart into convenient spots. We had a break apart and bridging different things with mental math strategies and so forth back in Chapter 3. This was one of the algorithms that we looked at for division, breaking things apart and looking at their pieces. So that's where it's coming back into play right now. So this one is yes. And the reason is because 17 divides 34 and 17 divides 51. It goes into both pieces broken apart evenly. So it'll go into the whole thing. Now if we try that same thing again with part B, the number is 19, and the original number we're trying to divide is 19,031. Is it going to work? It's not going to work. The 19 works, right? The first part's good. So the answer is no. And it's not because of the 19, right, when I break it apart. It's because of the 31. The 19 does not divide the 31. If it said 38, we'd be good, but it doesn't. So this is sort of a mentally observing whether something works rather than actually trying to do long division and make it work. That's not the goal. Okay, and your calculators are not a part of our discussion for the same reason that my 7th graders are not supposed to be using them. Right? It's true. All right, how about 2 times 3 times 5 times 7? Now our goal is not to multiply out 2 times 3 times 5 times 7, but to simply look at it and to decide if it will be divisible by 5. So what was our divisibility rule for 5s? Has to end in a 5 or 0. So you can think about it from that perspective if you wish. But you can also think about it from the perspective of what does it mean for something to be a factor or to be divisible by. So if you go back to our first definitions that we used interchangeably last class period, these were the 3 descriptions that I wrote down. And it's just a condensed form of what was written above and typed in. A number is a factor or divisor if the other number is a multiple of it. Right? A number is a factor or divisor if it is listed as a factor or divisor. So when we look at this example, whoops, one more back. We see 2 times 3 times 5 times 7. Is 5 a factor of 2 times 3 times 5 times 7? Yes. Yep, it's right there in the middle, right? So if we want to think about it from just a flat-out definitional perspective, the answer has to be yes, because 5 is a factor. It's listed out that way. Okay, so this is almost like somebody took a number and they broke it down into a tree diagram, right? Like, and they had all the pieces at the end. And at the end, each of the branches were a 2, a 3, a 5, and a 7. And you'd say, does it divide by 5? And you'd be like, yep, there's 5 right there at the end of our branches. The other thing you can think of, if you like it a little bit better, is that if you were to multiply this out, and you were to multiply something that had a 5 in it, then it would automatically end in 5 or 0. That's what happens when we multiply by 5. It's automatically going to end in 5 or 0, which means that the product, after all is said and done, will also then end, right, in something that's divisible by 5, because it will end in a 5 or a 0. So you can write it in any of those ways. So the one that I have written down is the first way that I described it. So yes, because 5 is a factor of 2 times 3 times 5 times 7. One other way that it occurs to me that you could think of it that might be helpful is that if it's something is a factor, it means that you have to be able to write it divisible by it. And do you see what happens to my 5s if I try? They cancel out, right? So all I'm left with in the numerator is 2 times 3 times 7, which is definitely a whole number. I don't get any remainder. So that's another way you could describe or think about this. But what happens on D? Yeah, you added 1 to it. So will it be divisible by 5? No. So this is a no. And the reason is because 2 times 3 times 5 times 7 is divisible by 5. And what that means is that it ends, this is one way of thinking about it, not the only way, but it ends in a 0 or a 5, right? And if you add 1 to it, it will mean it ends in what?
A 1 or a 6.
Yeah, it ends in 1 or 6. Well, if it ends in 1 or 6, it's not divisible by 5, right? I'll just put that it's by our rule, not. What if instead it said 2 plus 3 plus 5 plus 7 plus 10? I don't think I said that right. I think I said plus instead of times, didn't I? Did I say that? I wasn't listening to myself very well. 2 times 3 times 5 times 7 plus 10. That's what I wanted to say.
Yes.
That would work, right? If I added 10 to something, namely it's something that ended already still in a 0 or a 5, it would not hinder the ending part of it like the number 1 does. Cool. 24. We've already talked many times now about 24. I like the number 24 because it has things that work and things that don't, so it's a really good example to pull up. 24 divides something. Okay, so think about the 24s. Like you got 24 and 48 and 72. I think about 24 sometimes because cupcakes bake in sets of 12, right? But boxes of cupcakes usually come in sets of 24. 2 dozen. I don't know if you know that or not, but they do. So 24s is often on my mind with divisibility too. So you've got numbers that are divisible by 24. What are they all automatically also divisible by? Okay. Yeah, so generally speaking and specifically speaking, because some of you are coming from both directions. So Gracie mentioned 4 and 6. Somebody else over here said something about factors. Okay, cool. So Grace said all the factors of 24, and that's the general answer. So we want to actually list all factors of 24. So as we list all factors of 24, a really nice way to do it is like Gracie started us out, where we're doing them in pairs because you don't miss things as easily. So 4 and 6 work. You can also do 3 and 8. I've mentioned that one before. There's another one I've mentioned, 2 and 12. And there's one more pair, though it's extremely unexciting. 1 and 24. The reason I mention it is because 1 is still a factor. I mean, it is. So when we list all the numbers that it divides by, I need to include the 1, even though it's not exciting. I'm going to list it. So it divides by also all of those numbers. So 1, 2, 3, 4, 6, 8, and 12. And there's nothing special in this sense about 24. We could do this process no matter what number I was given, right? If I wanted to do the number 30, we could do that. We could do pairs of numbers, all the pairs of numbers that multiply to 30, and we could list them all out. All right, any questions on that? Yep, Hallie.
Why can't you divide it by 24? Because once you get
Oh, you can divide it by 24, but we already know it's divisible by 24 based on the description itself. So it says what other numbers?
Okay.
So if you listed 24, it wouldn't really be wrong. It would just sort of be like overkill because you already knew that one. That's why.
Okay.
All right, so every now and then your book likes you to take properties and it likes you to use them sort of in reverse. And this is an example of that where you're filling in the blank to make it do something instead. So we have the number 543,220 something. And we want to figure out what number has to go in the blank to make it divisible by 2, and then by 3, and then by 6. So we will start with the number 2. What numbers would have to go in the blank if we wanted this number to be divisible by 2?
Any even number?
Okay, so any even number. So somebody list them for me.
0, 2, 4, 6.
0, 2, 4, 6, and 8. Awesome. There we go. Missed mine. Cool. That's the easy one. The next one is a little bit more difficult. How would I find out the numbers that I need to be divisible by 3? Okay, I need to add what I've got so far, right? Okay, so I need to figure out what is 5 plus 4 plus 3 plus 2 plus 2. So what is this already with the sum for what the values are I do have? 16. So does 16 divide by 3? No. So I need to add something to it. What's the smallest thing I could add and get something divisible by 3?
1. Oh, wait, 2. Sorry.
It's okay. 2. Yeah, 2 will work. So if I put the number 2 in there, I'd have 16 plus 2, which is 18. There's more than that, though. What else could I use? Five. There's one more.
7.
Close. It's 8. 8 plus 16 would be 24. Yeah, so it's 24. I'd like for you to notice something else, though, because this is not unique. If you look between those numbers, what do you notice?
3.
It's an arithmetic sequence. We've seen those before. So once you get the first one, you can actually get the next two or whatever there are, depending on what you're working with, by adding 3 to get the next one, and then the next one. Yep,
Where
Hallie.
did you get 24? Why are we using?
We are adding whatever we're using here to the number 16. Because if I were to put the number 8 at the end of this, I'd have the same 16 I already had plus my 8, that gives me 24. 24 is divisible by 3, therefore the number with the 8 in that location will also be divisible by 3.
So we always, whenever it's a 3, we always take that total and subtract that from 24.
It's not about it being 24, it's about it being a number that's divisible by 3. So for example, if instead we had put the number 5 in here as one of ours is, if you add them all together, this doesn't give you 24, it gives you 21. 21 is divisible by 3. That's why 5 works. And the same thing for the number 2. If I put a 2 in here, I've got 18. 18 works because it's divisible by 3. So I'm trying to fill in the blank so that when I do the summation of it, I get multiples of 3. And 2, 5, and 8 work like that. So how do I decide, based on the work I've done so far, what numbers I would need for this to be divisible by 6?
The numbers that are in common with 2.
Yeah. So the numbers that are in common to both these lists, right? In order to be divisible by 6, it must be divisible by 2 and 3, both. This is a Venn diagram is all it is, right? What do they have in common? So what do they have in common?
2 and 8.
2 and 8. Good job. All right, so some more working with these sort of directional kind of questions. So these are going to be like trues or falses, and then justifying our answer as to the why. If a number is divisible by 5, can it be divisible by 10?
Yes.
It could. Can you give me an example?
20.
Sure. So 5 divides 20, and 10 divides 20. The operative word here is the word can. So on B, it says if a number is divisible by 10, can it be divisible by 5? First, starting with this part that says can it? Yes. And you can take, maybe you would use the example 40. 10 divides 40, 5 divides 40. Must it be? Sorry, I missed the must it be before. I apologize. I'll go back and get it in a second. Must it be?
For B?
For B. Yeah. Yes. And a really nice justification is because all multiples of 10 end in 0. And all numbers divisible by 5 end in 5 or 0. So the numbers that are ending in 0 would work. I'm so sorry, I skipped this one up above. The must it be here. So the can it be answer was yes. How about the must it be?
No.
That's a no. And so often when you're told the answer is, telling you the answer is no, you have to provide justification by way of a counterexample, right? So you need a counterexample that shows that a number is divisible by 5 but not divisible by 10. Emily?
So any number that ends in 5?
Yeah, any number that ends in 5 would work. So I think I heard some people saying 15. 5 divides 15, but 10 does not divide 15. Right? So it doesn't have to work that way. Mm-hmm.
So like, we have to explain it, can we just write that, and would that be counted as the counterexample?
Mm-hmm. Yep, it would. Okay, we have one last example.
Oh, sorry, Dr. Mann.
Yes, ma'am.
On part B, could we say that on like the must it be because 10 is a factor of 5?
You could almost say that. I think you want the word 10 as a multiple of 5. So yes, you could do that.
Okay.
Because 10 is a multiple of 5, all of the multiples of 10 will be included in the lists that are multiples of 5. You could say that for sure. All right. This is a fun example of real math like last time. It's not as complicated though. So a number in which each digit except for 0 appears exactly 3 times is divisible by 3. Okay, so they've got a couple of examples of that. 777,555,222 or 414,143,313. Okay, so every digit that's showing up in there shows up 3 times. There's 3 7s, or there's 3 4s, or there's 3 1s, and so forth. Everybody good so far with what they're saying? Okay. The question on part A says, explain why this statement is true. So there's a very interesting thing happening here. So whatever your number is, you have 3 times that number. That is not a hashtag, that is a number symbol. Okay? 3 times that number plus 3 times some other number plus, and you can do this as many times as you want. They did it in 3s, right? They did 3 7s, 3 5s, 3 2s. But they could have also done, just 3 7s and 3 5s, and it would be fine. Or they could have done 4 different numbers added together 3 times. Like they could do it in 4 of them. But what do you notice about every single one of these things as they're written here? They all have multiplication by 3. And if there's anything, and hopefully there is, that we learned when we looked at this problem over here for part C, if the number 3 shows up as a multiple of the number it is already, like as a factor of the number already, then it's divisible by that 3. Or in this case, it was the 5. But this 3 right here is showing up in every number, which means this piece divides by 3, and this piece divides by 3, and any other pieces also divide by 3. So therefore, they all, as in the whole thing, divides by 3. So I'll write that out in words. Each term is divisible by 3. So the sum will be 2. But we're going to look and see if it has to work. Not if it has to work all the time, but if it's the only way that this works. Must this statement be true in order for a number to be divisible by 3? In other words, must 3 digits show up within the number for the number to be divisible by 3 that match? No, it does not always have to happen. Can you give me an example?
21.
Yeah, 21 would be an example. Somebody said something else. What? 24 would be an example, right? Nothing repeats, in fact, right? But these numbers are divisible by 3, right? So what's happening in this description is it's a specialized type of number for which it's true that they're divisible by 3. And if you happen to notice it, you could identify that immediately. But it's not something that has to be always true for it to actually always work. Okay? So here's what we're going to do. Yes.
You lost room on the.
Okay, let me write a little bit more down. So 3 divides 21. Sorry, that should not have a line through it. 3 divides 21, and 3 divides 24, right?
Yes.
But I'll just use 21. Does not have 3 repeating digits.
Okay, so like repeating digits as in.
So the repeating digits don't have to happen in order to make it divisible by 3.
Got it. Okay.
But if they do happen, they create some things divisible by 3. So it's one of those things that it's it's enough if it works, but it's not a necessary condition to make something work. Okay, So here's what we're going to do. We're finished with this lesson, but I really want you to do group work in class. So we're just going to table all this, which means that you have an excellent opportunity between now and Friday to do your redos. So there better be some people turning it in on Friday, because I'm going to be really sad if it's not. Don't make me sad, okay? So we will do, this one I'll get back into my office hopefully to remember to switch it so that it says it's due on Wednesday next week, or Monday next week instead of on Friday. We will do the group work for this on Friday along with starting section 4 too.